Good morning, guys. Hopefully we got everything sorted out with the classroom situations and whatnot. If you can go ahead and give me a green check mark, thank you, Connor, and let me know you're with me, and then we'll get going. Mrs. Wood just had a few things, obviously, that she wanted to mention about foods and PE. So if you didn't sign in with Mrs. Woods this morning, then you would best probably just send her a message or something in Moodle or an email just saying what I miss. And that way you'll know what she was on about this morning. The second thing, and the thing that I want to start class with today, is finishing up Unit 5. So last day I left you with some balancing questions. I left you with the remainder of the Unit 5 learning guide. And today I wanted to go through any problems you guys had and any questions you might have about the Unit 5 learning guide. And assuming everything kind of goes according to plan, I was hoping you would have the Unit 5 learning guide in today, by the end of the day sometime, and I can get it marked and get you guys a password out for that test, and you can write it over the next few days, hopefully before the weekend, because this Unit 6 only has 2 sections and it's going to go very quickly, and it's just more of the same, essentially more balancing and chemical reactions. So there you go. Did anybody have any specific questions about the Unit 5 learning guide, or questions about balancing, any of the extra practice stuff, anything like that? I would love to go through those, but if not, we'll just move on to Unit 6. I know a few people have submitted, oh sorry, I said Unit 5, I meant Unit 4. A few people have submitted their Unit 4 stuff already, and it's gone very well so far, so thank you for those of you who've got it in. So I'll open up the Unit 4 learning guide, and if you have any questions, don't feel like you're the only one with the question. There's probably a few other people who have similar questions to you. So anything from the balancing stuff that I kind of left you with at the end of last day? Anything from there at all? Yeah, Costin, we're going to need to be specific about what question you would like. You can give me like a page number or give me the equation or something like that, and I can go through it. And then if nobody has any questions, we can move on. Page 32. What is the first reactant there? Costin, what does the equation start with? My 32 is probably different than your 32. Fe. E. I'm thinking this guy here at the top. Let's see if we can't do these guys. All right. Let's start with the top one. So again, we identify what reactants we have and we identify what products we have, and they're always going to be the same. So if we start with iron and oxygen on the reactant side, so the left side of my arrow, I'm going to end with iron and oxygen. Now, it sounds silly, but sometimes you'll be given questions where they're already balanced. Some equations just work out that they're balanced. You don't have to do anything. But that doesn't happen very often. So what we want to do is we want to count all of the elements we have on the reactant side, and then count them on the product side, and then compare. And if they're different, then we need to balance and add coefficients in front. So iron on the reactant side I have 1, and oxygen there are 2. And on the product side I have 3, and oxygen there are 4. So now that I've identified my reactants products, I can see that they're clearly not balanced. So I have 1 iron, 3 irons. I have 2 oxygens, 4 oxygens. So I need to balance these guys. The first thing I come across is iron. I have 3 on my product side and only 1 on my reactant side. So what I'm going to do is I'm going to put a 3 here, and that is going to change the number of irons I have from 1 to 3. So now my irons are balanced, 3 and 3. Oxygen's the next thing that needs to be balanced. My reactant side, I have 2, and on my product side I have 4. So I need to address that, and I have O2 there, so if I put a 2 in front of it, I get 2 groups of 2, which is 4. So that changes this from a 2 to a 4, and then I have 4 and 4. 3, 3, 4, 4, she's balanced. How's that work for you there, Costin? The 3 on that page, like the third question, or the 3 in the one we just balanced? Third question. So there's the first, second. This one with the bismuth and the oxygen and the hydrogen. Okay, let's do this one as well. Same process as always. Identify the elements that are present. I start with bismuth, Bi, O, and H. If I start with them, I end with them. So I just write them down on the other side. Then I count. So I see that I have 2 here. Oxygens I have 3 of, and hydrogens I have 2 of. And on the other side I have 1. I have 1 and 2. All right. Now, we kind of wrote down some rules when we first started balancing. We said if an element's by itself, we should probably leave it till the last. And it's just going to be more efficient that way. So I can balance the BIs first, or I could leave them to the end because they're by themselves. The thing that I'm going to run into a problem with is my oxygens. Because I look at my oxygens, I have 3 on one side and 1 on the other. Which is a bit of a problem. Not that big of a problem, but well, let's just, I think it's going to work out. Yeah, it'll work out. So let's balance our bismuths first. It doesn't matter. So I have 1, I need 2. So I'm going to put 2 there, and that changes the 1 to a 2. All right, the next thing I have is this oxygen. I have 3 on my reactant side and I have 1 on my product side. So I need to put a 3 here. That's going to change that from a 1 to a 3. And my hydrogens, they get affected because I put that 3 there. I'm going to have 6 hydrogens. 3 groups of 2 is going to give me 6. Now I need to go back to my reactant side. I have 2 bismuths, 2, I have 3 oxygens, 3 oxygens, I have 6 hydrogens, and I need 6 over here. So what do I have to multiply by 2 to give me 6? I'm going to have to put a 3 in there, and that's going to give me 6. 6 and 6. Balance. So 2, 2, 3, 3, 6, 6. Everything looks good. And there we go. So the process is the same for all of them. The last 2 questions are both what we're going to learn about today. They're both combustion reactions. They're really tricky. I was very impressed with those of you who submitted your Unit 4 learning guides already. You did the last few, and you know they're hard. So well done. Is there anything else from this learning guide that you would like to see done, go through? Questions about? If not, I'm moving on. Nothing? Okay. As I asked you last day to print off that Unit 6 learning guide, we're going to skip Unit 5, and we're going to come back to it after we do 6. I know we kind of jump around a little bit. Just in my brain, it makes a little bit more sense to do it this way. So the Unit 6 learning guide is on chemical equations, and we, as scientists and people in general, like to classify things. So you don't say, oh, I like listening to just music. Well, there's lots of different types of music. There's country music and rap and classical and jazz and pop and indie rock and all this other stuff. So we like to classify things as humans. It's just human nature. And we do the same thing with chemical reactions. And the reason we like to classify these is because if we can figure out what classification to give it, we can put it in a group, we can actually predict what's going to happen, which is pretty neat. So just knowing the reactants, we can say, oh, that's this type of reaction, so this is going to happen, which allows us to predict what's going to happen before we actually even, do the reaction or do the experiment. So we're going to look at, trying to think, I think there's 6 or 7 different types of reactions, and they all have different names, and you should be able to identify them and figure out what they are called. Now, a couple of the names are really kind of straightforward. Synthesis, maybe a bit trickier, but when we synthesize something, that means we take stuff and we put it together. If you synthesize something in music, you're taking different instruments and you're putting them together to make a song or something in that regard. A synthesis reaction in chemistry takes 2 different reactants, so 2 things by themselves, and we mix them together and we produce a compound. So basically we're just forming bonds between these things and they stick together and combine together. So the example here is sodium and chlorine. If I took a bunch of solid sodium and I mixed it with some chlorine, they would form together to produce something which is salt, NaCl. So the 2 individual elements we start with, they combine together and they produce a compound, NaCl. Another of the same sort of example, magnesium and oxygen produce magnesium oxide. So nitrogen gas and oxygen gas join to form dinitrogen monoxide. We can, instead of writing the skeleton equation, we can just give you a word equation. So this is what synthesis looks like. These are sort of different ways to represent the same thing. So 2 or more reactants combined to form a product. So that's how we can say it in words. Just a general equation, A's and B's acting as variables. You have an A, you have a B, they stick together and you get AB. A specific example, sodium and chlorine, an analogy, and a picture. So this is synthesis. I'm going to just jump over to the learning guide just to make sure that everything is somewhat close to the learning guide. So then synthesis, yes. All right, sorry, I just forgotten what the learning guide looked like and I just wanted to make sure it was similar. All right, so here's 2 examples. We have magnesium and nitrogen, just 2 elements hanging out by themselves. And remember nitrogen, and then the next example we have fluorine. These are both diatomic. So when they exist by themselves, they're always going to be N2 and F2. And remember on the periodic table, we had that little 7 that it made. We had oxygen, nitrogen, oxygen, chlorine, fluorine, bromine, and iodine. Those all combine together to kind of hang out with one another, always diatomically. So it's really important when we put them down in a chemical reaction, we write them as N2 and F2 and O2 and I2. All right, so we have 2 examples here. Magnesium plus nitrogen are going to react, and we don't know what it's going to produce, but we can identify this as a synthesis reaction because we have 2 individual elements that we're starting with. So they're going to combine together to produce a compound. Now, we know what the compound is going to look like because magnesium and nitrogen can only combine in one way. And that's not what I wanted. That's not what I wanted. That's what I wanted. All right, so magnesium on the periodic table, I'll just jot down a little note below it here. Magnesium on the periodic table is Mg, and I'm pretty sure it has a charge of +2. And then nitrogen is N and has a charge of -1. I want to say 3. I'm going to have to double check both those. Going off the top of my head, bring out my trusty periodic table. Magnesium +2, nitrogen -3. I got lucky. All right, so these two things are going to combine together. Now, I've discussed the crisscross method, or you can just think in terms of charges and multiples of these things, but essentially I'm going to have a compound that's formed, and it's going to look like Mg3N2. So the 3 comes down from the nitrogen, the 2 comes down from the magnesium, and I end up with magnesium nitride. That is all that happens. That's the only possible thing that can happen when we begin with 2 elements. So they can't combine in any other manner. The nitrogen isn't going to come first because we always put the metal first. So literally that's the only thing that can happen, if that makes any sense. The next example here is aluminum and fluorine. I'm going to do the same process. I'm going to say, okay, aluminum is Al, has a charge of +3. Fluorine is F, that has a charge of -1. And then I'm going to combine them, crisscross if you like. I'm going to get Al, F3. Now, I guess we could run into some issues here where you're thinking, Mr. Borden, on the reactant side, or the left side of the arrow, there was 2 fluorines, but now we have 3. What happened? And this is a very common place students will get confused. Same with the example up above. The magnesium, there's only 1, and the nitrogen is 2. You got to remember when we combine elements together, a metal and a non-metal, they can only combine in one way. So this is why we balance. Now both these examples aren't balanced. We could go back and say, okay, how many of each of these things do I need to balance this out? But when I have aluminum and fluorine combined together, they only combine together in one way. That's 1 aluminum for every 3 fluorines. I can't make it combine differently than that. That's the only way it works. So this is why we balance once we've done these types of equations. Does anybody have any questions on that one? Are we okay? So we're going to do a whole lot of these. All right. We'll go back to the notes. All right, so the second type, the first one was a synthesis reaction where we took 2 things and stuck them together. This is a decomposition. Now we've used the word decompose before in biology, and does anybody remember what a decomposer does? Because it's the same thing in chemistry. Decomposition. A decomposer is something that eats dead or decaying things. It takes like a plant or an animal and it breaks it down into nutrients and things like that. And that's what a decomposition reaction is. Same idea. You're taking a compound and you're breaking it apart. So the really easy way to recognize that you're dealing with a decomposition reaction is that you're only starting with one thing and it breaks apart. So we have the analogy here, AB breaks down into A and B, where A and B are separate elements. We can take the same example of sodium and the chlorine. Sodium chloride, we can break it down into sodium and chlorine, its individual parts. It's really interesting, I always find it's interesting, that sodium chloride is table salt. We eat it in all of our food, and it's, you know, a tasty little thing. It's on pretzels, it's just delicious, sodium chloride. But if you take sodium, metal, and it'll like, you add it to water, it'll explode and light on fire. And if you take chlorine, like just think when you go in a swimming pool and you get some chlorine in your eyes get all red and itchy. That's really diluted chlorine. Like chlorine is very nasty stuff. Sodium, really nasty stuff. But you mix them together, you get table salt. It's just yum. So there you go. The second example is hydrogen, dihydrogen monoxide or water. If we take dihydrogen monoxide and we put a little electricity into it, it'll break down into hydrogen oxygen gas. So we can take water and we can break it into hydrogen oxygen. And this is you know, something that car manufacturers have looked at for turning just plain old water as fuel into hydrogen oxygen. Both hydrogen and oxygen gas are highly flammable. So we could just, fill up our tank with tap water when we get home and then, cruise down the street and burn the hydrogen oxygen. When you burn it, it just produces water again. So unfortunately, it takes a lot of electricity to break down the hydrogen oxygen, not a super efficient reaction. So it kind of takes a little bit more energy than you get out of it, sort of thing. All right, so we have one thing we start with, one reactant, and it breaks into two products. And the specific equation, NaCl breaks down into NaNCl. And you can see this one here is balanced. Or we have the couple breaks apart, or we have a circle and a square, and they break apart into a circle and a square. This is decomposition. So this is the exact opposite of a synthesis reaction. Synthesis, two things coming together to form a compound. Decomposition, one thing breaking apart to form two individual things. Does anybody have any questions on decomposition? Let's look at a couple examples and predict what's going to happen. So we have AuCl, gold chloride and potassium oxide, and we're going to try to figure out what is being produced. Does anybody have any suspicions about what we're going to produce when we break apart gold chloride? What are we going to end up with there? And what is going to happen with potassium oxide, the K2O? Guesses? Anyone want to guess on the gold chloride one here? What are we going to do? What are we going to end up with there? So we're going to have two things, and they are going to be separate. So we're going to get chlorine. Yeah, Jenna, for sure. Thank you. So we're going to get chlorine. And chlorine is one of these special ones. It's one of the magic 7. When it's by itself, it's always going to be Cl2. But Mr. Borden, on the other side, it was Cl3. I know, but that's why we balance, because gold and chlorine only can combine together to form AuCl3. But when chlorine's by itself, it's always Cl2, which is slightly confusing. We're also going to get gold, which is Au, which looks like that. So this isn't balanced. We could spend time balancing it, but that would take a long, long time. So let's just go to the next one. We have potassium and we have oxygen. We're going to end up with two separate things. Yeah, Costin, exactly right. Chlorine, when we have it by itself, it'll always be Cl2. Never, ever, ever will it just look like Cl. And maybe I can find a periodic table here to draw on. There we go. Let's erase some of this stuff. Just a reminder on the 7 elements that when they live by themselves, they are always diatomic. So we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And these 7 elements, kind of hard to see, I'll circle them in red. We call them the magic 7. See how it kind of makes a 7 on the periodic table? But look, if I count them, there's 1, 2, 3, 4, 5, 6. So there's only 6. So the 7th is hydrogen hanging up by itself at the top here. And when these guys live by themselves in a chemical reaction, they're always diatomic. So it's always going to be, wow, this computer was working so well for so long. Now it's causing me trouble again. So they're always going to be H2 or Cl2 or F2 or O2 when they live by themselves. Costin, it's a good question. The ones with the Roman numerals, they don't have Roman numerals on the periodic table, but when we name them, we need to include the Roman numerals. And those are the multivalent metals. And you can see I've actually written that here. We were talking about it before. Multi is more than one charge. Something like magnesium only has one charge. It's always +2. That never changes. But if we look at something like molybdenum down here, number 42, it can have a charge of +2 or it can have a charge of +3. And we need to figure out which one just based on what it's combined with and how it's combined. So there are a ton of metals in the interior of the periodic table in the purple bluish section here. You got these guys, 2 charges, 2 charges, 2 charges, 3 charges, 2 charges, 2, 2, 2. There's some more guys down here. These are all double charges there. And these are all the multivalent metals. So you can see that they all have more than one charge. If you are using any of those and you're trying to name them, then you need to name it with the Roman numeral to indicate what charge you're dealing with. And it's not the first or the second, it is whatever charge it has. So if you're dealing with iron and it has a charge of 3, it would be iron 3 with the Roman numeral 3. All right, so let's jump back to the example we were dealing with here. So we had potassium, which was K, and then oxygen, which was O. So it's in a compound. If it breaks the compound apart, we're going to have K by itself, and then we're going to have O by itself. But O and Cl are both in the magic 7, so they have to be Cl2 and O2 if they're by themselves. They're diatomic. All right, let's look at an example here. This is one that I want to look at. The one on the bottom here, I have H2O2. Does anybody know what H2O2 is? You probably have it in your house, actually. This is why it's really important when we name covalent compounds, we name them properly, because H2O2 is kind of like H2O. There's just an extra oxygen. H2O is one thing, that's water. Water you can drink, you can swim in it. It's great. H2O2 is really, really nasty stuff. If you get it on you, it can hurt you. It can burn your skin. It can like bleach your clothes and stuff. Has anybody ever heard of hydrogen peroxide? Oops. Does anybody have hydrogen peroxide in their house? Mr. Ross does. Sometimes hydrogen peroxide is used to, in like a first aid kit, or in your bathroom you probably have it maybe. If you get like a cut or something. Yeah, Kaylin, you can use it to clean wounds out. And the really cool thing about hydrogen peroxide is that it's H2O2, so it's really close to water. And when it decomposes, it breaks down into 2 different things. And one of them is H2O, which is water, and the other is oxygen gas. So it sterilizes the wound. So if you have a cut, say you cut your hand, your parents probably, when maybe you're little or maybe you still use it, if you put the hydrogen peroxide on the wound, the H2O2 is really very reactive. It's likes to react with just about everything. So it's really good at killing bacteria. So it'll kill the bacteria. And then what's left over, if you put it on a cut, it'll kind of bubble and you'll see little bubbles form. Those bubbles are oxygen gas being formed, and then you have some water left over. So that's why we use it on cuts, to kind of clean cuts out. Now the stuff you have at home is likely about 3% to 8% in there somewhere, hydrogen peroxide. So that means if you have a big liter bottle of hydrogen peroxide, a couple 300 milliliters of that big bottle is actually hydrogen peroxide. The rest is just water. They dilute it so it's not really strong. Now I, as your local neighborhood science teacher, have some hydrogen peroxide here. And this stuff is 29%. Really, really nasty oxidizer. It can do really not nice things to you. So let's play with it, hey? Why not? I'm going to put on my safety glasses. Unfortunately, I forgot my safety glasses at home. It's kind of like when you forget your PE strip and you got to wear like the stuff out of the Lost and Found. That's what I'm doing today. So here we go. Put my safety glasses on, safety first. Well, these are hard to see out of. All right, so I'm going to step over here And I'm going to bring out our plate and this graduated cylinder. And then I'm going to actually just grab a glove. I probably should have brought some towels, but I forgot to do that. Has anyone seen this demonstration before? It's called Elephant's toothpaste. Has anyone seen Elephant's toothpaste before? Yeah, it's a pretty good one. All right, so I'm going to put on this glove again. Forgot my gloves at home, so I get to wear a medium-sized glove, which doesn't really fit too well. So this is hydrogen peroxide. I'll just pour a little bit into the bottom of the graduated cylinder here. It's a completely clear liquid. And it's H2O2, so it's pretty similar to into water in appearance, but it's not very nice. You don't want to get it on your skin. If I had gotten some on my skin, I've got it on my skin before, it turns your skin white, so it just kind of like basically kills all the dead skin cells and stuff on the outside. And you can see it right there, right now. It's decomposing. Isn't that amazing? It's the best science experiment you've ever seen. So what's happening right now is that you have hydrogen peroxide in here. It's this clear liquid. And basically there's oxygen being produced, and that oxygen gas is eventually just going to evaporate out of there. And then we also have some water there. So if I left this long enough, it would eventually just turn into water and all the oxygen gas would escape. And I'd be left with a little graduated cylinder of water, which is fun and all, but it's not that exciting. So what I'm going to do is I'm just going to pour a little bit of this out. I'm going to pour it into here. I'm going to do it in this one. Oh, this one had some stuff left in it from last time. So you can't really see it there on the bottom. What I'm going to do is I'm going to add something called potassium iodide. And what potassium iodide is just a white powder. And that potassium iodide is going to help the oxygen be produced. So you can see in the graduated cylinder here, you can see it bubbling away there. And those bubbles are just kind of, bubbling away. Away they go. There you go, making a big mess. Jeez, Mr. Borden, you're making a giant mess in the studio. All right, so you can kind of see, I don't know if you can see really well, but there's steam coming off the top of it, and it really gets quite warm. So we've taken that hydrogen peroxide and we've, broken it down into water and some oxygen gas, which was pretty interesting, kind of bubbled up. Now you can see right here, I have my trusty sunlight. If we do the same thing again, which of course we're going to have to do it again, just put this underneath here. If we do the same thing again, this time I'm going to put a little bit of soap in here, because this soap is going to help the hydrogen peroxide. It's going to help the hydrogen peroxide trap those bubbles, that oxygen gas that's produced. So I'm just going to mix it up. All right. So instead of pouring the potassium iodide in that powder form, what I've done is just taken that potassium iodide and I've just mixed it with some water. And this is called a catalyst. It just kind of speeds up the reaction and just makes it happen a lot faster. So if I left this, the oxygen would eventually, be produced, but that's really slow and we don't have time for that sort of stuff. So what I'm going to do is I'm just going to add a little bit of this potassium iodide. It's just going to make the reaction happen a little bit faster. So you can see initially it turns this brown color, and that's the iodine being formed. And you can see that these bubbles are slowly being formed, and the bubbles are that oxygen gas being produced. And as the hydrogen peroxide breaks down, we end up with this fun. And it's called Elephant's toothpaste because it kind of looks like toothpaste. Normally you can use really fun colors and make it all stripey and whatnot. And it's just going to keep going until it makes a huge mess. Maybe turn it a little bit. And again, all of these bubbles are going to escape my plate. All of these bubbles are just oxygen gas, and the oxygen gas is just being trapped in the sunlight. And it'll eventually take all of that hydrogen peroxide and break it down into water and oxygen gas. And I don't know, can you guys see the steam, the evaporation that's coming off the top of that? I wonder if I can have, I don't have any paper around here. Yeah, you can see it. Yeah, so it's quite warm when I touch it. It's warm. When I say warm, it's maybe like about 40 degrees or so Celsius. It's not like hot, but it's warm enough to evaporate the water that's in there. And you can see what's produced here on my glove. You can see how it's really this brown color, and that's just the iodine that's being produced in the reaction. It's not actually being produced, it's just a catalyst, so it's being used up. So just the iodine makes things kind of stained and brown. You can see the plate on the edge is brown, and the paper that the first experiment kind of splattered on turns this really stained color, and that's what can happen to me and has happened to me now that I'm covered in the iodine. So that's elephant's toothpaste, also known as potassium iodide, helping hydrogen peroxide break down. It's a really pretty interesting reaction to look at, and I will play with it more when we do the speed of the reaction next day. We'll do it again and we'll see how fast we can make that happen. There we go. Get out of there. Safety no longer necessary. Yeah. There we go. So that's hydrogen peroxide. So we took hydrogen peroxide. Because it's really concentrated, it breaks down into water and oxygen. And again, that's probably about 10 times the concentration of the stuff you might have at home. So there you have it. Let's go back to the notes and we'll look at the next type of reaction. So far we've looked at synthesis reaction, which was two things coming together to form a compound. Then we looked at a decomposition reaction and the example there that we just did. Now we're going to look at a single replacement reaction. Now a single replacement reaction, this is where things get a little bit more complicated, but still not terribly difficult. I don't think any of these are super difficult. Basically, when you have a single replacement reaction, single replacement is single is one, and replacement, something's being replaced. So what's happening is we have an element by itself and a compound, and the element that's kind of hanging out by itself is going to kick something out of the compound. If it's the metal that's hanging out by itself, it's going to kick the metal out of the compound. If it's a non-metal that's hanging out by itself, it'll kick the non-metal out of the compound. And this is what happens. We have an element and a compound, they react together to produce a new element and a new compound. So looking here, we have A plus BC gives us B or AC, and then A plus BC gives us C and BA. You have an element by itself, compound, kicks it out. I think the two examples down below here, aluminum foil in a solution of copper 2 chloride produces solid copper and aluminum chloride. So we have aluminum, which is Al, and copper 2 chloride is CuCl2. So now this aluminum's by itself, it's hanging out by itself, and it's a metal. And it says, hey, I want some of the action. So it says, I need to kick something out of this compound. So it's not going to kick the non-metal out, because if it kicked the non-metal out, then we'd have copper and aluminum trying to combine together, but they will never combine because they're two metals. So that doesn't work. So instead of the copper and the chlorine sticking together, the aluminum's going to kick the copper out. Now the copper gets kicked out, now it's by itself. So you can see Cu hanging out here by itself. And then we have aluminum and chlorine now formed a compound. And again, we need to be careful of how these things form compounds. Aluminum had a charge of +3 always, and then this was copper chloride, CuCl2. And just trying to think if that works out. Anyways, you get aluminum chloride produced. The same thing can happen, but instead of having a metal hanging out by itself, we could have a non-metal. So we have fluorine. And that fluorine is going to, because it's a non-metal, it's going to kick the iodine out of the compound. It's going to kick it out. So iodine's by itself, and then we have Na and F. So fluorine kind of, sorry, my mouse is in a different spot on my screen. So the Na and F, the sodium and the fluorine combine together. So just kind of another summary, whatever analogy or picture or whatever you think works best for you. Think about it that way. There you go. And let's look at two examples. So we have PbCl4 and NaCuO2. All right, PbCl4 plus Al. Looking at the first example here. So aluminum hanging out by itself. Aluminum says, I want to be part of this compound. It has a choice to kick out the metal or the non-metal, and because the aluminum is the metal, it's going to kick out the metal, and Pb is the metal. So it's going to say, Pb, see you later. So Pb says, okay, I'm going to hang out by myself. The lead. So I'm going to end up with two things. The Pb was kicked out, it's now by itself. And then what I'm left with is aluminum, which always has a charge of +3, and the chlorine, which always has a charge of -1. So the aluminum is going to combine with the chlorine to produce AlCl3. Same thing down below. We have another metal hanging out by itself. Sodium says, hey, one of you guys has got to go, and the copper says, I'm a metal, I'll go. So we're going to end up with copper by itself, and then the sodium is going to combine with whatever's left, in this case oxygen. Now oxygen's always -2. Sodium is always +1 from the periodic table. So if I crisscross, I'm going to get Na2O. So sodium is taking the place of the copper. All right, I have another little demonstration to show you on this one, and that is the one that was actually right out of the notes. So we have copper 2 chloride, CuCl2. Has anyone ever heard of copper 2 chloride or seen copper 2 chloride or played with copper 2 chloride before? Not quite as common. Maybe if you see it. I have some copper 2 chloride here. It's this really neat sort of turquoisey blue color when you dissolve it in water. Has anyone seen this stuff before? No one. Yes, Josh B. Costin. No. All right, so that's copper 2 chloride. I'm just going to set that aside. Copper 2 chloride. I'm going to mix it with some aluminum. I just so happen to have some aluminum right here. This is just plain old, kind of ironic that we call it tin foil, aluminum foil. And I'm going to predict what's going to happen. So aluminum, just Al by itself. What do we think? So we have copper 2 chloride, which is that blue stuff. We have aluminum, which is just tin foil. And tin foil is a terrible word. It's now called aluminum foil. I guess it used to be tin years ago, probably before I was born. Does Mr. Ross remember when tin foil was made of tin? He does, indeed. He remembers when tin foil was made of tin. All right, so what's going to happen? Can anyone predict what I'm going to end up with here? I have a metal, aluminum, and it's going to take the place of something in this copper 2 chloride solution. And I'm going to produce, two things. That's going to end up with something, a compound, and then something by itself. So what's the thing by itself? What is the aluminum going to replace in the compound? What do we think? Any ideas? What's going to be kicked out of the compound? What's going to be by itself? Copper. Josh? Nailed it. Which isn't to be confused by nails, which are mainly made of iron. So yeah, copper is going to be, by itself. And then what am I going to be left with in the compound there? So the aluminum is going to replace the copper. The copper kind of gets kicked out. Perfect. Aluminum is always +3, and chlorine, because that's all that's left, the copper got kicked out, I'm left with the chlorine. The chlorine's always -1. So I'm going to end up with AlCl3. 3. Now, we're actually going to do this, or I suppose I'm going to do the reaction. You guys are going to sit there and watch it. But the reaction says I should end up with copper being produced. Does anybody know what copper looks like? Anyone think of some copper that they've encountered in their everyday regular lives? What can you describe copper? It's kind of an orangey brown color. Pennies are plated in copper. They used to be pure copper, so if you have a really old penny, it's pure copper. But then copper started to get expensive, and then it was costing about a cent and like 1.2 to 1.5 cents, depending on the price of copper, to make a penny. So they stopped making pennies out of copper, like the full penny, because it was just too expensive. So theoretically, we should mix our copper 2 chloride and our aluminum together, and we should be producing some copper. And that copper, you guys have all said, okay, we have copper pots, we've seen the stuff as pipes, it's brown, kind of an orange color, and that should be what happens. So again, safety first, my lost and found goggles. I kind of like these. Have a little bit more of an impact than just a regular, safety goggles that I might have at home or actually do experiments with. I'm going to do my super secret shift over here. All right. So aluminum foil and copper 2 chloride, I'm going to mix them together and we'll see what happens. Probably should have brought a pencil or something. Here I have one. Use Mrs. Ward's. Do not tell Mrs. Ward I used her pencil in the copper 2 chloride. Okay, I'm just going to sink it down so we get a little more contact happening here. All right, so I'm just going to leave that for a second. And it might be a bit hard to see, getting a bit of glare off that light. Tip it back. Maybe it's not so bad. So right on the front, there's some bubbles being produced on the surface of the aluminum foil. Maybe a bit hard to see it. Maybe if I'm really quiet, I might be able to hear it. All right, so I'm just going to give that a second. Let it sit there. I didn't mix the copper 2 chloride super strong. Maybe while we're waiting for that, this is what copper 2 chloride looks like as a solid. So actually, when you first mix it with water, it's a green color, which is really neat because it changes from this kind of greenish brown color when you mix it with water, this really nice blue color. And it's a really beautiful blue. You can get some really nice blues. So that's what copper 2 chloride anhydrous looks like before you do anything fun with it. And this is kind of just slowly plugging away here. Let's see if I can use Mrs. Ward's pencil again. Some tongs would have been a great idea, but I didn't think that far ahead. Pull that out of there just for a second. So on the surface, it kind of looks almost like tarnish, but all of that browny orange stuff that's there is copper, and even in the bottom of the beaker, can't see it super well. There, you can see it a bit there. So in the bottom of that beaker, you end up with a bunch of copper being produced. So normally when I teach, I wear my wedding ring, and today I took it off because this copper 2 chloride will actually do this exact same thing with any metal. Just gonna try to get this in frame for Mr. Ross there. Beautiful. Oh, look at that. That's perfect. That's a great close-up. So I could take any metal. I could take my ring, which is made of titanium. I could put it in there, and this solution would take all of the titanium in my ring and convert it into just copper powder. And I could do the same thing with a nail or basically just any metal. I could put it in there, and I could just dissolve it and basically make metals disappear and change them into just copper, really. So I don't think my wife would be super impressed by me if I showed up at home with a handful of copper powder instead of my ring, but there you go. So you can see it bubbling away. When you actually touch this, the beaker does get a little bit warm. It's an exothermic reaction, so it means that the bonds are being broken and a little bit of energy is being produced. And yeah, my ring would be worth less. The nice titanium ring that I have would be just copper, which would be kind of sad. So there you go. I didn't mix it super strong. Maybe we can do it again in a few days, mix it a little bit stronger. You can still see it bubbling away down at the bottom there. Just showing you that the reaction's occurring. What would happen if you put gold in there? I've never done gold, but I would assume the exact same thing would happen. It would actually, the gold would be put into the solution, and the copper would still come out. So if we jump back to the computer here, we'll look at how this progresses here in a second. If I did the same reaction, so let's take the same reaction, and instead of mixing aluminum in, which is easy to come by and not terribly expensive, if I did gold, AU. There are rules based on the reactivity of metals and things like that, and how much energy is needed to make a reaction occur, but assuming this reaction would occur in the first place, what would happen? So the gold would be, replace the copper, so we'd still end up with copper, and then we'd have gold, which is AU. I always forget the charge of gold. It's always not one we use a lot because it's really expensive. I'm going to have to look it up. Gold. Gold is either 3 or 1. I don't know which one. We'll pick the 3. And let's go with AuCl3. So if we put gold in there, we'd get a solution, and that solution would look kind of like what's there, but we'd end up with gold chloride. So the actual gold would bond with the chlorine, and it would be dissolved in the water, and it would just be in the solution there. We wouldn't be able to see the gold. It wouldn't be shiny anymore. It wouldn't be special and gold. It would be actually mixed into that solution. And then we'd get copper produced as well. So the copper would actually show up. If I leave this reaction going for long enough, it's still kind of progressing away here. Use Mrs. Ward's pencil again. You can see that it's kind of broken down into 2 pieces now. And what's going to happen is eventually this solution, it won't be clear anymore, or sorry, it won't be blue anymore. It'll go to a clear color. And basically all of the copper 2 chloride will be used up. And instead of copper 2 chloride, what I'll have left is I'll have this aluminum chloride, which will be dissolved in the solution. So all this aluminum metal that started as tinfoil will now be dissolved in the water. And I'll have all this solid copper left. And if you were really good at chemistry, which I'm not, I could go back and I could, reverse the reaction and take the aluminum out, and I could make aluminum metal again if I reacted it with some other things. I don't know how to do that, but I could. If I put my finger in there, I don't really want to put my finger in there. Nothing would really happen. It's not highly reactive to skin. Skin is carbon and stuff like that. Nothing really going to happen to my skin. Although I could end up with it on my skin, and then maybe I put my ring back on, or I, pick up something metal like all sorts of wires and whatnot around here. That copper 2 chloride would probably start to eat away at the metal that's there. You guys mentioned gold. I have Mr. Ross's like adapter here. It's gold plated. I kind of tempted to put it in there, but I won't do that because he might just make me disappear. So Leeds, I'm not going to do it, okay? Stop peer pressuring me, Leeds. That's why we don't give copper 2 chloride to students very often, because it's just like, stick your finger in it. What would you do if gold was in it? Just do it for science. All right, so that is a single replacement reaction. I really like that one. Drink it, that's the other thing. It looks like Kool-Aid, Mr. Borden. It is not Kool-Aid. It would make you very sick. Not a good day. Very bad day. All right, so we looked at those 2 examples. Mr. Borden died because he drank copper 2 chloride today in the studio. Good day, hey Costin. No more science! Mr. Borden dead. All right. That was a single replacement reaction. One thing by itself, it kicked out whatever was in the compound. In this case, the aluminum kicked out the chlorine, or the copper, sorry, and the copper ended up being produced. A double replacement reaction is the exact same idea, except instead of having one thing by itself in a compound or two things, you end up with two things, and they just kind of switch. They switch partners, which is kind of interesting. I don't have any good examples of double replacement reactions, unfortunately, but we'll just continue on. So this one's a little bit more involved. There's two compounds, so you need to crisscross your charges with two different things, and it's a bit tricky. This is kind of as tough as it gets. The other ones, the last two, are pretty straightforward in my opinion. So when you have two compounds react with one another, they just switch partners. So the metals will switch and the non-metals will switch, and they'll just bond with the other things. So let's look at some examples of this. You can talk about it in terms of kind of a general equation. You have AB and DC. The A and then the C combine, and then the D and the B combine. So that's one way to think about it. Or a specific example, magnesium chloride plus beryllium fluoride, and they switch. So the magnesium was with the chlorine, but it says, I'm done with you, chlorine, and it's going to combine with the fluorine now. And then the beryllium, which was with the fluorine, says, okay, we're going to switch. And then the beryllium's now with the chlorine. Or you can think about it as like a partner swap at a dance, trade partners, and then the picture, if that makes more sense to you, circles and squares and what have you. So let's look at a couple examples of this. So CaS, calcium sulfide and sodium hydroxide. Pardon me. I'm just going to grab a drink here. And then we have potassium phosphate and magnesium iodide. And we're going to see how these things switch. Okay. Let's jump over to OneNote, do a couple of examples. All right, so there are the examples on the right here. Oh, don't want to give it away. Although I will keep those charges up just to make my life a little bit easier. All right, so first example, CaS plus sodium hydroxide. They're switching partners, and this is where it's really important to remember that we can't ever have two metals combining together. They both have positive charges. It just wouldn't work. So I'm never going to end up with the Ca and the Na stuck together, like CaNa. Two metals. Can't do it. So that only leaves one other possibility. I'm going to have the Ca combine with the OH, and then I'm going to have the Na combined with the sulfur. Now I can't just write down the elements. I have to make sure I get my charges are all right and balanced here. And calcium is Ca, it's plus 2 always. And then OH is hydroxide, and off my polyatomic ion sheet, that OH is always minus 1. And then I have sodium, which is Na is plus 1, and sulfur is minus 2. So if I crisscross my charges, I'm going to end up with Ca1OH2. Need to put that in brackets as to not confuse the 2 with anything else. And then I have Na, and then the S gives it its 2, and then I end up with a 1 down here, but I don't include the 1s. And at this point I could balance if I wanted to, but I don't because I'm lazy. It just takes too long to do it all. So there you go. The metals have swapped essentially metal with a metal, and I end up with two new compounds. The same thing can happen down below. This one's a little trickier. I'm going to end up with the potassium and the Mg, magnesium, switching. So you can see that I have that started up here already. So K is always plus 1, so I'm going to have K potassium iodide, Ki. And remember potassium iodide, that's what we used already today. We had, here's my potassium iodide that we used with the elephant's toothpaste. And potassium iodide, as I mentioned before, Probably won't be able to see it at the bottom there, but it's just kind of like a white powder. So that's what potassium iodide looks like. You mix it with water, turns this kind of light yellowy color. It's potassium iodide mixed in water. Potassium's +1, iodine's -1, so those crisscross, and I just end up with K. Get the eraser going here. K is +1, iodine -1. That one's done. Crisscross, that's what it ends up as. And Mg is magnesium's +2, phosphate's PO4 -3. So when I crisscross, this one's a little trickier. I'm going to get Mg, the 3 comes down from the phosphate, and then I get this PO4 group, and I'm going to put it in brackets and bring the 2 down so I don't end up with Mg3PO42, which would be quite confusing. So there's a double replacement. That's tricky. Those ones are probably the hardest ones you're going to encounter. But I think you guys can do them. Capable. All right, what do we have left? Good question. We have neutralization reactions and combustion. So we have 2 left. And the last 2 are, I don't know, the last one's easiest. This one is maybe a little bit tricky. We haven't talked about acids and bases yet, but these words you've heard of before. Now, normally if we followed the course, unit 1, 2, 3, 4, 5, 6, 7, 8, we'd encounter unit 5 before 6, and unit 5 talks about acids, bases, and salts. But we skipped it because I don't like doing it in that order. So an acid, you have acid in your stomach. You probably have dealt with acid before, like vinegar, common acid. Acid is really easy to identify because acids always begin with H. So if you have a compound that starts with H, it's an acid. HCl, hydrochloric acid, that's stomach acid. You can end up with all of these different types of acid. H2SO4, sulfuric acid, that's really common in like car batteries. And a base is really common in household cleaners, sodium hydroxides like bleaches and like toilet bowl cleaners. These are all full of hydroxides. So if something ends in OH, it's a base. So H, OH, that's how we identify these things. So if it begins with H, it's an acid. If it ends in OH, it's a base. And one really cool thing that happens when we mix an acid with a base is they mix together and we end up with salt and a water being produced. Essentially salt water. So if you have a strong acid and you want to neutralize the acid, kind of like if you had upset stomach, heartburn, you want to take an antacid. What is that? It's just a base. So you're eating a base, kind of like chalk or something. You swallow it, it goes and neutralizes the acid in your stomach, and it produces a bunch of water, and it produces some salt. So phosphoric acid helps to neutralize compounds that cause rust, such as iron 2 hydroxide. So we can use science to do these types of experiments. So obviously we haven't talked about this. We'll spend a whole chapter talking about acids and bases, and you'll be experts at them by the end of Unit 5. But for now, an acid begins with H. HCl, hydrochloric acid. HBr, hydrobromic acid. HF, hydrofluoric acid. Bases end in OH. NaOH, sodium hydroxide. CaOH, calcium hydroxide. SROH, strontium hydroxide. Salts are, we call table salt a salt, but a salt is actually a category of compounds. So all ionic compounds, or almost all, are salts. So NaCl, that's table salt. That's what we put on our food. CuCl2, copper 2 chloride, that really fun stuff that we were playing with earlier, stuff, that kind of brownie stuff. That's a salt. A salt that I wouldn't want to eat, but it is still a salt. Copper 2 chloride. Sodium, copper and chlorine together, metal, non-metal, salt. All right, so I think this one's really cool because you take the H from the acid and the OH from the base, you mix them together, and H and OH together, HOH. It's going to give you some water. We've written it as HOH just to make it obvious that the H and the OH are coming together, but we'd normally write that as H2O, and H2O is just water. And then whatever's left, you're going to end up with a metal and a non-metal. Those are going to stick together, and you're going to call it salt. So let's do a couple examples of this, and then we'll do combustion, and we'll call it a day. I know I've gone on a little longer than I normally would, but we're almost done, so we'll just stick with it for another minute or two with me. Never just a minute or two, I know, but carry on. Seem to have misplaced my pen. Got it. All right, HBr and NaOH. So I see the HBr and the OH. I know I'm dealing with an acid and a base. And again, we take the H from the acid and the OH from the base to give us HOH, which is just H2O, water. And then we're going to add to that sodium and bromine. That's what's left. So Na is +1, Br is -1. I'm going to have NaBr. So I have NaBr and H2O. And these all work out the exact same way. The next one's the same deal. I have an H, I have an OH. HOH is H2O. And then what's left? Well, I have a magnesium as my metal and a phosphate as my nonmetal. So magnesium, Mg is going to be +1. PO4 phosphate is going to be -3. So I'm going to get Mg 3PO4. That's what's going to happen with these guys. These are going to be a little bit more difficult to recognize until you get into Unit 5 and you're really confident with acids and bases. But for now, acids start with an H, bases end with an OH. You have acids and bases. One last type of reaction, combustion. And that's just burning stuff. And combustion reactions are the hardest to balance just because they usually end up with this kind of weird, odd, even scenario. So combustion reactions occur when you have a hydrocarbon. So hydrocarbon, like I'm a hydrocarbon, but I wouldn't want to burn me, so we're going to avoid that today. A hydrocarbon is something with carbon and hydrogen stuck together, and the number of H's and C's vary depending on how long of a chain you have, but you could have methane, CH4. You could have butane, like in a lighter. Gasoline is a really kind of long hydrocarbon with some other stuff tacked onto the side. C2H2, that's like glucose. Different types of sugars. Sugars definitely burn really well. And there you go. So the really cool thing about hydrocarbons is when you burn something like wood. Wood is a tree. A tree is made of cellulose. Cellulose is a hydrocarbon. Just all living things are basically hydrocarbons. And when you burn trees, you burn wood when you have a campfire, you're producing carbon dioxide and water. It's kind of really weird to think when you burn something, water is produced, but it is. So when you encounter a combustion reaction, it's like a gift from the science gods. They say, okay, what is going to be happening in this hydrocarbon reaction? So if you can identify that you have a hydrocarbon, which is carbon and hydrogen stuck together, and oxygen gas, O2, as your reactants, the products are always going to be the same. It doesn't matter what hydrocarbon you're starting with, you're always going to end up with carbon dioxide and water. So it doesn't matter what hydrocarbon you have. You could have CH4, you could have C2H6, you could have C3H8. You can burn it, it's going to produce carbon dioxide and water all of the time, 100% of the time. There you go. Let's look at two examples of these. What do you think is going to be produced? Hydrocarbon, oxygen. We're going to end up with the same things. Here's the two examples over on the side. C4H10, this is the guy we're looking at here. We are going to produce carbon dioxide and water. And same thing down here. And they are always the same. Always going to produce carbon dioxide and water. Anytime you burn a hydrocarbon. That's it. That was a lot of material to take in, and I know that it goes really quickly, and I apologize for that, but it is what it is. So let's look at the learning guide real quick, and then I'll leave you guys for today. Basically, we've done all of these notes. We've gone through all of this stuff, and then there's some practice. So these definitions, general equations are kind of like the stuff that I gave you today in the notes. So you should be fairly good with those. Double replacement, neutralization. And then there are some examples down at the bottom here. So question number 2, all the way through the alphabet almost. They give you different types of reactions, and they ask you to identify them. And for now, I'll tell you what, for next day, I'd love it if you came back with the different equations just identified. And you can just write SYN for synthesis or DR for double replacement. It asks you to balance them, but for now, let's not worry about balancing these. I just want you guys to focus on the types of reactions. Let's look at an example here. Let's look at letter L. It has Fe and O2. I have 2 things that are by themselves. This is a single element, and then I have another element, 2 single things. 2 single things are combining together to produce a compound. So I'm starting with 2 things, and I'm ending with 1. And this is starting with 2 and combining them together to produce 1. This is going to be a synthesis reaction. Costin? I can indeed. What I would like you to do, Costin, though, is to go back and look at the different reactions. Is there single replacement, double replacement, synthesis? So there's 7, 6, 2, 4, 6, is there 6 or 8 types of reactions, and see if you can identify them on this chart. There's 26 of them. Go back, look, see if you can find one that kind of matches, and then see if you can identify it. The tricky ones are going to be like this guy here, like O. I see it starts with an H, ends with an OH, and produces water. So this is going to be a neutralization. Because I see that I have an acid and a base to start with. So once you kind of get going, you'll see the patterns start to emerge, and it'll get into a habit, and you'll just start to be able to identify them really easily. So look at the examples that we've given you, see if you can match those examples up with anything out of the work for this section. So that's that. Next day, we're going to go through the second part of this lesson, which is rates of reaction. We're going to play with the hydrogen peroxide a little bit more, or I'm going to. When I taught at OKM, I got it to blast out of the beaker I was dealing with and hit the ceiling. I've yet to hit the ceiling in this room, so we'll see if we can get the ceiling next day. I don't know how Mr. Ross feels about that, but science, I guess. We can only do what we can do, right? So we'll talk about rates of reaction, but it's really important that you guys finish up Unit 4, because Unit 6 is going to be done on Friday, and we don't spend a ton of time on Unit 6 just because it's not, it's a lot of stuff, but it's more balancing and reaction stuff that we've been looking at. So go through this. Next day, I'll start with any questions you might have had out of the first part of Unit 6. And then we'll move into the second part, and then we're done Unit 6 next day. So just 2 sections, a quick one. Unit 4 needs to be done. It's due. Make sure you have Unit 4 submitted, hopefully by the end of today, and have that test written, because things are going to start to pile up here pretty quick. So that's it for me for now. If anybody has any questions, I'll go through them. But if not, I will I'll leave you guys for now and see you guys on Thursday. All right, have a great afternoon, guys. See you on Thursday. Bye-bye.